So before elaborating how we embed our function field into the adele space, first I want to give a couple of remarks from the literature. The first thing, you can also come across for the same structures, you may also come across adele ring, indeed, which denotes the same structure we consider the adele space. So that means they also have the ring structure, but in this course we are not going to going to need to consider their ring structure. And you may also come across the keyword like repartition, but this is more related to periodic completion, which is considered in the chapter 4, and this will be also the out of our purpose for the moment. And the other notion we can introduce inside of the adele space is a kind of generalization of the Riemann-Roch spaces of a given divisor. So let me remind you, we define a Riemann-Roch space which contains the functions whose principal divisor is bigger than or equal to given divisor A. So that means they contains the functions with prescribed poles and zeros, and indeed we can denote this set by using discrete valuation maps. So that means Vp of x is bigger than or equal to Vp of A for all places P in the function field F. And indeed, we can generalize this notion into the adele space with respect to a fixed divisor A, and that contains the adeles such that their valuations is bigger than or equal to Vp of A for all places in the function field F. So that means at each component, if we for the functions at each component, we take their valuations, they are going to behave like the functions in the Riemann-Roch space. But in this case, the only difference is that we can have different functions at different components. But for the moment, let me also explain the adele space, which is associated to fixed divisor A, is also forms a vector space over K, or a subspace of A of F, because obviously this is a subset of the adele space. And in order to see their vector space structure, let me consider a non-zero constant C and an adele alpha so that means Vp of alpha P is bigger than or equal to Vp of A for all places P. Then our claims that again this component-wise scalar multiplication is also an element in the adele space which is associated to the divisor A. And since the valuation stays the same under the scalar multiplication, we can easily see that this scalar multiplication is also element in A of A. And if you consider two adeles such that whose valuations are bigger than or equal to Vp minus Vp of A. We can see that their summation is also adele in A of A because Vp of alpha beta. So that means the valuations of the functions at their pth components. Of course, we consider the component-wise addition. In this case, when we apply the triangle inequality by our assumption, indeed, we can see that valuation of this sum is also bigger than or equal to Vp minus A, and this gives us, this is also element in A of A. So at this point, let me elaborate the previous observation which I tried to give. For instance, if we consider a function in the, okay, we can embed our function field into the adele space, and in some sense we introduce the notion, the adele space, which is associated to the divisor A. And indeed, if we consider a function from the Riemann-Roch space of a given divisor A, and when we look at its principal divisor, indeed we can see that this is an element in the adele space of the divisor A. So indeed, the adele space of a divisor provides more information than what we have for what we get from the Riemann-Roch spaces. And indeed, by this observation, we can interpret the Riemann-Roch space as an intersection of the adele space, intersection of the function field. So by the intersection of the function field, we consider all principal adeles. And this is in some sense the infinite copy of the L of A, but this is essentially the Riemann-Roch space, or essentially itself. And the second observation is that, so F can be embedded in the adele space, and we also consider another vector space, the adele space, or the vector subspace of the adele space, which is defined by a given fixed divisor A. And since two of them are vector space, their summation is also subspace of the adele space. And here there are vector spaces over K, but it's easily to observe that they are infinite dimensional vector spaces. Over K. So there's still no advantage or there's still no way to get to work with some finite dimensional structure. But the next theorem, and this is going to be our main theorem in this lecture, and in the remaining of the lecture, we will try to understand how it proofs look like. And this theorem tells us, even though these structures are infinite dimensional vector space over K inside of a function field F of genus G, the quotient is going to be finite dimensional vector space for every divisor A, and indeed exactly we can compute its dimension, and this dimension indeed, which is denoted by I of A because it will have a spatial name. This integer is nothing but the dimension of the Riemann-Roch space of this divisor minus its degree plus g minus 1. So it's kind of similar statement or the similar equations which appears in the Riemann-Roch theorem. And later we will see that why we have these similar statements. But before explaining this theorem and before elaborating its relation with Riemann-Roch theorem, indeed we will define this dimension of this quotient space as index of the specialty specialty of a divisor A, and indeed if it is equal to 0, so it's not going to be spatial for us. So that means if I of A is 0, that means its dimension is equal to its degree plus 1 minus g. So that means when the degree is large enough, we know that this index of specialty is going to be 0, and in this case A is not going to be spatial for us. So that means we are interested in for which spaces we don't have this equal, so which divisors are spatial, and this is kind of this index of specialty is kind of measurement for the divisors. And indeed we can before giving its proof, let me a bit elaborate how we can restate this theorem which can be related with the statement of the Riemann-Roch theorem. Indeed, if the dimension is equal to, dimension of this quotient space is equal to this quantity, this means that the dimension of a Riemann-Roch space of a divisor is equal to its degree plus 1 minus g plus the dimension of this Riemann-Roch, the dimension of this quotient space. So indeed, this will be the proof of this theorem will be the first step to understand the statement of the Riemann-Roch theorem. And indeed, thanks to this interpretation, we can redefine the genus in terms of the index of specialty. More precisely, the index of the specialty of the zero divisor which is the dimension of its Riemann-Roch space minus its degree plus g minus 1. So that means the genus can be seen as the index of specialty of the zero divisor.